All right, so in this pre-lecture video, we're going to talk specifically about chemical kinetics. So chemical kinetics drive a lot of what we do when we design environmental engineering processes, so it's really important to understand these concepts prior to moving forward throughout the rest of the class. So chemical kinetics is concerned with the rate at which reactions occur. So how fast is this reaction moving forward? So in class, we're going to be talking about what we call irreversible single-phase reactions that are uniformly dispersed in media. So what you'll see on the left side of the screen is a single-phase system. So you only see orange dots. We're only in the gas phase or the liquid phase or the solid phase. We're not intermingling between phases. You'll also see that we have an irreversible reaction. So we proceed from A to B, but B does not go back to A. So irreversible, it only goes one direction. And you will see that it is uniformly dispersed. So that means that those orange particles are evenly distributed throughout whatever media we're in. In contrast, to give you a visualization, on the right side of the screen, you're going to see a reversible multi-phase reaction that is not uniformly dispersed. So you see that there are orange dots now and there are purple dots. So let's say the orange is a gas and let's say the purple is a liquid. So now it's multi-phase. There's two things going on. The reaction A to B is also proceeding both forward and backwards. So it's an equilibrium reaction and it can go back and forth. You'll also see that we're not uniformly dispersed. We've got gases stuck to one side of the container and stuck to the other side of the container. So it's not a uniformly distributed media. So those are the things that we care about when we talk about kinetics in this class. We're assuming that reactions are irreversible, single phase, and uniformly dispersed in a media. So in water and wastewater treatment, we're typically going to see what we call first order reactions, and we'll go over what that means later in the coming slides. But before we go there, the first thing I want to do is I want to make sure that we define our variables. So if we're going from a concentration of some variable called A, a reactant A that moves towards products, C0 or C0 is going to be an initial concentration of A in units of milligrams per liter. C is going to represent the concentration of A at some time t in the future, again in milligrams per liter. K, which is a little k when we see it in our equations, is going to be the rate constant. So that's a concentration per unit time, so milligram per liter per whatever time. So time could be minutes, it could be seconds, it could be hours, whatever type of time that we want to use, as long as we're consistent. And then the differential, dC dt, is a rate of change in concentration over time. So again, that has units of concentration per time. So milligrams per liter per unit time. And again, that could be seconds, minutes, hours, whatever type of time that we need in our system. So if there's any one big takeaway that I want you to take from this kinetics lecture, it is this slide. This is the slide that you should print out, take notes on, whatever works for you, and make sure that you understand everything that's going on in this slide. In this class, and predominantly when we talk about chemical kinetics in water and wastewater treatment, we talk about three different types of reactions that we can have. The first is what we call a zero order reaction. So in this particular reaction, the rate is independent of the concentration of A or the products, and the disappearance of A with time is linear. So basically what that means is that as time changes and concentration changes with time, it's related to the rate constant. So that's what you're going to see in that third column, the differential equation column. So that dC dt, remember, is a change in concentration per time, and that's related to K. And we have a negative because we have an amount and a concentration that's decreasing with time. So that's why it's a negative. If we were to integrate that particular equation, you would cross multiply so that you have C's on one side and T's on the other. This is from differential equations. And you would integrate from the initial concentration to the final concentration at a specific time t. And if we integrate, we get the equation that's in that final column on this table. So you're going to get the concentration at some time is related to the initial concentration minus the rate constant times time. So linear relationship. Now, if you recall from the last slide, zero order is probably not going to be seen that much in the real world, but first order is going to be the most important when it comes to water and wastewater treatment. So in first order reactions, the rate is proportional to the concentration of one reactant. So you can have multiple reactants going on in a system, but it's proportional to at least one of those reactants. So what that looks like in terms of a differential equation, if we say that differential equation in words, it means that the change in concentration in time is related to the rate constant times the concentration at a given time. So if we change that into an integration and we integrate, you'll see now that the C is in the bottom. And if you remember and you integrate and you have 1 over something, many times that becomes a natural log. So this becomes a logarithm. So what you'll see in that final column is that the natural log of the concentration at a given time t is equal to the logarithm of the concentration initially minus the rate constant times time. And that might not be the easiest equation to use, but one that you've probably seen before that comes directly from this is C over C naught is equal to E to the negative KT. So that's just rearranging the top equation. And this is very common, right? This is exponential decay, basically, is what's going on here. It's saying that as we start from a given concentration, we're decaying along a logarithm over time in the system. And then finally, one of the other type of reaction that we could see in water and wastewater treatment, and you may see in other systems that you may design in the future, is a second order equation. So in this equation, the rate is proportional to the second power of a single reactant to a single product. Now you could have multiple reactions and multiple products, but when we talk about second order, we're talking about one reactant going to one product. So you'll see I have in parentheses there, 2 of A gives you 1 of P in this system. So you'll see in the terms of the differential equation, the change in concentration with the relationship to time is now related to the rate constant times the concentration squared. And so same process that we did for the other types of reactions. We integrate, we move all the C's to one side, all the T's to one side, and we integrate, and you'll see that the equation that we get looks a little bit different. You'll see that the final equation we get for a second order is 1 over C equals 1 over C naught plus KT. So again, this table is super, super important. It's really important if you're an environmental engineer. You will definitely see this on the FE exam. Civil is probably not on your FE exam, but you will see it a couple times in this class. So it's really important to kind of know these equations. So again, if you're going to highlight and bold one particular slide from this pre-lecture, make sure it's this one. So for those of you who aren't maybe auditory learners and it's hard to understand what's going on in rate kinetics, just by hearing me say it, it might be nice to look at the screen and kind of see these different types of reactions that we have. So what you'll see in the top left is a zero order reaction. So on this particular plot, we're plotting concentration on the y-axis and time t on the x-axis. And you'll see that we started a specific concentration, C naught, and over time we have a negative slope. And that slope is going to be your rate of reaction. It's a negative K. So here we're plotting concentration versus time, and this is the zero order reaction. Now, if we want things to be linear when we look at the first order reaction, which is on the right side of your screen, we instead of plotting C and T, we now have to plot the natural log of C and T. So you saw this on the last slide that our equation for a first order is related to a logarithmic decay. So you'll see that we start at a concentration of a natural log of the initial concentration, and we have a same kind of decreasing trend over time, and that slope is negative KT. But here we're plotting natural log of C versus T, so that's a little different. And you'll see that I've starred this graph because, again, first order reactions are the ones that we're going to care about the most in water and wastewater treatment. And then finally on the bottom left, you're going to see a second order reaction. So instead of plotting C and T, we're now plotting 1 over C and T. And you'll notice that this goes up. It's got a positive slope over time, which is a little bit different because, again, now we have 1 over C instead of just C itself. In every lecture that you're going to see as a pre-lecture, I like to have a key concepts slide. So what are the key concepts that you need to know about a specific technology? So in the terms of kinetics, we're just going to go right back to this table. So I'm not going to spend too long going through it again because we did talk about it in previous slides, but please do be aware of all of these equations, really understand what's going on in this table. Don't be afraid to ask questions in class. I'm happy to answer, but these are really the key concepts that I want you to pull out of this particular lecture. So some other key components related to kinetics. One of the things that's really important about kinetics is that most chemical reactions increase and decrease the rate of reaction with relationship to temperature. So the rate of reaction moving forward increases or decreases based on temperature. And most of the time, as temperature increases, we're also going to have an increase in the rate of reaction. So that's really important. So hopefully something that you've seen in past civil classes, I hope in Civil 321, when you took kind of an introduction and principles of environmental engineering, is what's called the Arrhenius relationship. And so what this relationship shows is it shows that the rate constant of a second reaction is related to the rate of reaction of a first reaction times what we call theta, which is a temperature coefficient. It's usually 1.072. And that theta has an exponent of a change in temperature. So this particular relationship basically tells us how to get rate constants if we know one rate constant and two temperatures. So if we know, let's say, for example, K1 at, let's say, 10 degrees Celsius, but we want to know K at 25 degrees Celsius, we can find it using what we call the Arrhenius equation. So this might be a nice relationship to just be aware of in the future. You may end up seeing on a homework. It's definitely on the FE if you're an environmental engineer, so it's a really good concept to know when it comes to kinetics. The other thing you're going to see in a lot of these slides for pre-lectures are what are the key parameters engineers need to know, right? So a lot of things that we talk about are going to be theoretical so that you understand how it works, but we need to know why it's important as engineers as well. So I like to have this slide in here because I'm the person who needs to know why. So why is kinetics important if you're an engineer, right? So some things that we need to know is we need to know the order of the reaction, right? So is it 0? Is it first? Is it second? What order is it, right? The other thing, if we're designing systems and we have chemical reactions, we need to know what's the rate of reaction. And the reason that we need to know the rate of reaction is that reactors are often designed to remove a specific chemical or contaminant from water and wastewater. That's generally the goal in that kind of a setting. And so we need to know how fast that chemical is going to be removed from a specific type of system. And so that's related to the rate of reaction. So we're going to need the reactor to run for a certain amount of time to get from the initial concentration C0 to that final concentration C. So we need to know the amount of time that it's going to take for the reaction to occur as well. So these are key parameters, and this is why we care about them in water and wastewater engineering. So again, most reactors aim to remove a specific amount of a chemical. So we need to know C0 from a measurement, right? So that might be you as an engineer going to a water or wastewater treatment plant and measuring an initial concentration entering the system. So you may go to a groundwater well or a surface water source, and you may go measure what's going on in these systems. And then many times, if you know the rate of reaction or you know the amount of time that it's going to take to move through the system, you're going to need to then calculate a final C. And many of the times when we're calculating a final concentration, the final concentration is a goal. So in the United States, we have regulations about what is allowed in our water and our wastewater, and we'll talk about these in more detail as we move forward. But many times there's a goal of a certain amount of a concentration that we need to be below in order to be safe. So many times if we have an initial concentration, we know the final concentration we want to get, and we have a rate constant, it's about optimizing for time, right? And so the amount of time that water is in a specific type of reactor is going to be important. And time is related to all sorts of other variables that we'll talk about in the future. But this is why it's important as an engineer to understand kinetics, because many times we have an initial concentration, we're targeting a final concentration, and how we get between the two, that's one of those equations on the slides that we've talked about. That's one of the calculations that you may have to do in order to understand what's going on in the system. So to sum it all up, what's the purpose of kinetics? Why do we need to know anything about kinetics? Kinetics is going to allow us to properly design water and wastewater treatment systems to achieve specific removals of chemicals or contaminants of concern. So that's the ultimate goal, right, of what we do in water and wastewater engineering, and kinetics is very fundamental. So that's going to wrap up our kinetics pre-lecture. Make sure that you've taken some notes. In class, we're going to talk a little bit more about these concepts. I'll give you time to ask questions, so please bring questions if you have them, and then we'll walk through some calculations so that you can see how this is applied in practice.